This is a question that asks us to find or show that there is a point in the 2D plane which is equidistant from these 4 points. This, and this. Oops, yeah. So you have these 4 points, and you need to show that there exists a point which is equidistant from all of them. The other way to look at this is that all these points they lie on a circle. If we can show that, then we have essentially answered the question. So let us assume that there is in fact a point, say x comma y in space, which is equidistant from all the points. So let us find out the distance between x comma y and the first point. So the distance would be x minus am1 square plus y minus a by m1 square. And if you do that for the other points, that is this and this, you will still get a similar equation up till and until the last point, which kind of gives you a different form of equation because the values of m1, m2, and m3 are kind of used in a reciprocal manner to what they were used before. But the idea is, and if you really look into the geometry of the question, that all the points in fact lie on a hyperbola. Because if you notice that the points, they satisfy the following equation, x comma y equals a square, all of them. So in reality, what we are doing here is we're actually looking at points on a hyperbola which coincide with a circle of some radius. And that radius is actually given by the distance square, or just the distance. So this radius is in fact equal to this value that we intend to find out. So a more general way, and this is what we call as a parametric way of representing a point lying on a hyperbola, is that the point takes the form am by and a by m. So this is a general point on a hyperbola for all m. I think that is what makes this a general point. We can take different values of m and we will be moving along this hyperbola at all times. So, since all the points lie on a hyperbola, we can assume that all of them are of the form am and a by m. In the first case, m is nothing but m1. In the second case, m is nothing but m2. In the third case too, m is nothing but m3, so that is pretty obvious. But in the last case, m is actually 1 upon m1, m2, m3. So that's different value. But nevertheless, it's still not in the hyperbola, and we can do whatever we choose to do, considering that all the points lie in a hyperbola. With that in mind, and that's a very key observation in this question, what we can do is we can evaluate the distance squared for a random point. So we can get rid of the subscript 1 and evaluate the distance from all the points on the hyperbola. So now what we can do is we can evaluate the distance between certain points on the hyperbola and the center of that hypothetical circle. Let us assume that the radius of the circle is in fact r. So that means the distance that we were measuring is just r. And we can simplify this equation as r squared equals x squared plus a squared m squared minus 2amx plus y squared minus plus a squared by m squared minus 2ya by m. We can make this a function of m, like so. And we will see that if we multiply the entire equation by m squared, we get m to the 4th, and the coefficient is a squared. Then we get, so m to the 4th comes from there, and then the next higher power would be m cubed. And let us evaluate the coefficient of that. M squared is here. We should have an m somewhere, which is here. So we get the coefficient to be minus 2ax. Similarly, we will have a coefficient for m squared. And m squared will pop up when the denominator is independent of m, which is in this case, and in this case. So we get y squared plus x squared minus r squared. And we also have a coefficient for m to the 1st, or just m, which we shall get if we consider this term, and that coefficient is 2ya. Lastly, we get an m independent term, which is just 1, and the coefficient in that case comes out to be a square, and this equals 0. So we have essentially reduced the problem to solving a biquadratic equation such that the coefficients are like so and so, a squared for m to the 4th minus 2ax for m to the 3, this for m squared, this for m, and the coefficient being a square. Now, if we can solve this biquadratic equation, we will get all the points, and we can show that they would satisfy point A, point B, point C, and point D. But the clever way and a more quicker way to do this is to see what the product of all the values of m would be. So at this point, we started with random points on the hyperbola because we did not specify any condition for m. But as soon as we fix our r, that is the radius of the circle, we end up limiting the possible values that can satisfy this equation. And that limits to only 4 values of m because you have 4 as the highest coefficient. So that means you will have 4 roots to this equation. 4 roots means you shall have 4 points lying on the hyperbola, which will intersect with a hypothetical circle of radius r, and you can go to any radius r and you shall always get 4 such points that ultimately lie on the circle as well as the hyperbola. Now, the diagram may be a bit misleading because if we consider a hyperbola of this sort, we are forgetting the other branch which lies in the 3rd quadrant, and the circle in fact turns out to be somewhere here that intersects both the arms of the hyperbola, and in this case I'm just showing that it's to intersect with just one of the arm. That might be the case, but most likely that's not true. In any case, theoretically, conceptually rather, this is exactly what's happening, that the circle is intersecting the hyperbola. So with that information in mind, let us calculate the product of all the roots. So we know that the product of all the roots turns out to be, since the coefficient of m to the 0 is a square, that will be a square divided by the coefficient of the highest power, which is a square. Now, as the highest power is also 4, and since that's even, we really don't need to add negative sign here, and everything balances out, so the product itself is 1. That means if to this equation, or rather to this equation, we had 4 values of m, m1, m2, m3, and m4, then the product of those values that intersect with the circle and the hyperbola is in fact 1. So here we already have the first 3 values of m, that is to say we already have the first 3 points on hyperbola. What about the last point? What is the m value for the last point? Well, using this relation, we can say that if we have the first 3 points, the last point, that is m4, will have to be 1 over the product of the first 3, m2, m3. And we see that that is, in fact, the case here. Because if this is m1, m2, m3, and this is m4, the product of all the m's turns out to be 1. So we have shown that these m's, in fact, satisfy this condition. And that is to say that they satisfy the condition that is asked in the question, which is that they lie on a hyperbola, that means they are of this form, and they're also equidistant from a random point in space, which turns out to be the center of the circle.